Hi everyone, we are on 5.4, day 4, and this is going to be solving logarithmic equations. So before, we were solving exponential equations, so equations where an exponential term was present and eventually we needed to use taking the log of each side, or natural log of each side. This time though, we are actually going to start with equations that have logarithms in them and learn how to use our knowledge of exponentials to solve them. So let's first talk about the how. We will raise both sides so the bases are the same. Like we did. When writing inverses. So this will have a heavy connection to some of our prior knowledge, which is great. Before we can start looking at some examples, we do have some notes to take because we have to keep in mind what the graphs of logarithmic functions look like, and that's not actually something that we've done a bit of yet. So let's talk about vertical asymptotes. So logarithmic graphs have a vertical asymptote. Log functions have restrictions on the domain. Because a vertical asymptote exists. At x equals 0. And this is because we can't take the log of 0. It does not exist. Now if we make a connection to our exponential graphs, let's do a little sketching so we can visualize why this is. Let's say I was looking at y equals 2 to the x. I do not see a k value. Remember, k determines our asymptote. We have like an invisible plus 0 right there. So this means I have a horizontal asymptote at y equals 0, because k, our k value here, determines our asymptote. And if I were to do a quick sketch of that so we can see it, here's my asymptote at y equals 0, and I know that this is growth because b is greater than 1. So left to right, this graph would be increasing. So here we have an exponential graph. The inverse of exponentials are logarithms. So the inverse of y equals 2 to the x, if we were to switch x and y and solve, which we do know how to do, we would arrive at the equation y equals log base 2 of x. This graph will have a vertical asymptote at x equals 0. Let's see what this would look like. X equals is always a vertical line. And this graph looks like so. Now, why the graph looks like this, we'll be discussing later. But notice the connection. Now, we know that exponentials and logarithms, when we look at their equations and do the algebra, are inverses. But notice these graphs. If we were to literally switch x and y for all of the ordered pairs on the x-axis, we would actually get all the ordered pairs on the y-axis. And if we were to switch all of the x, y ordered pairs on this graph, we would arrive at this function. So exponentials have a horizontal asymptote at 0. That does not affect the domain. Does not affect domain. Because when I go left to right, negative infinity, come in from the right, positive infinity. So the domain here would be all real numbers. But this, now that I have a vertical asymptote I need to concern myself with, does. Affect domain. Here, I would have to say when I come in from the left, I can be anything except 0, and then to the right, I'm all good. So in terms of our domain restriction, what would we write? Bring back our domain knowledge. We would have to say our domain for this graph would be all real numbers, x not equal to 0, or we could say negative infinity to 0, parenthesis, union, 0 to infinity. So because restrictions do exist, this is going to actually mean something when we are solving our algebra. Because if we get a value for x, we have to make sure that that x value is not the location of the asymptote. Keep that in mind. We'll come back to that thought in a little bit. To summarize our little discovery here, so because of this, when we solve, remember I just mentioned it's going to affect our process at the end. We'll write it first and then see what it looks like when we do some examples. There may be extraneous solutions. If you have your highlighter and you want to highlight that vocab term right there, that would be good. Super important, so we would give it its own exclamation point. This means we will, so must, always check answers. When solving log equations. We are now ready to start looking at some examples. The directions are very simple. Solve. Number 1, log base 3 of 5x minus 1 equals log base 3 of x plus 7. Look at our how at the beginning of our notes. We will raise both sides so the bases are the same, like we did when writing inverses. So when I'm considering log base 3, I want to say to myself, hey, I know that the inverse of log base 3 would be to raise both sides with 3 as the base. So I'm going to raise both sides. Notice how careful I am to really make sure that that blue 3 that I just wrote is huge and that this all is clearly part of the exponent. No confusion. Space is your friend. Use it. Again, over here, being really clear that that's a huge 3, and then this is up high and smaller. 3 and log base 3 cancel. 3 and log base 3 cancel. So that leaves behind 5x minus 1 equals x plus 7. Quick note for those of us who might like this. This is perfectly fantastic to show for work. If you notice that we have log base 3 on the left and log base 3 on the right, if you're able to mentally reason, well, as soon as I raise both sides with the base of 3, that's going to cancel and that's going to cancel, I am okay if you jump from that first step to this third step. Those of us who it really helps to show our brains that in-between step, please, please, by all means, do this first and then come here. To finish, we're going to solve for x, so go ahead and press pause. You finish solving for x. When you press play, you will see the solution for what x equals. Press pause. Welcome back. I hope we are matching with our answer, x equals 2. Now my question is, are we done? Well, thinking back to that note we just wrote to ourselves, because logarithmic equations and logarithmic functions, have vertical asymptotes, that means that we do have domain restrictions where there are certain values of x that are not okay. We have to double check, is that value of x okay? So that's why we must always check our answers when solving log equations. So off to the side, let's do our check. We're going to be plugging back into our original, so log base 3 of 5 times 2 minus 1. Is that equivalent to log base 3 of 2 plus 7? Remember, for a check, we're looking for left equal right. So simplifying inside parentheses, 5 times 2 is 10, minus 1 is 9. So we'll get log base 3 of 9 equals, and on the right side, 2 plus 7 is 9. Let's see, log base 3 of 9 equals log base 3 of 9. Check. I'm in good shape. So this solution is real. Moving on to number 2. There we go. Number 2, log base 5 of 3x plus 1 equals 2. Now I do not have log base 5 on both sides, so I can't do that whole mental, when I raise this side base 5, this side base 5, etc. That's not going to work because I only have log base 5 on one side. But that's okay. To solve this though, the process is the same. The inverse or opposite operation of log base 5 would be to have 5 as a base and raise it. So it's going to be 5 to the log base 5 of 3x plus 1. And what we do to the left side, we have to do to the right. So this will be 5 squared. I'd ask that you press pause from here and challenge yourself to finish solving for x. Remember to make this 5 visibly humongous. I mean, don't be crazy, don't take up half the page, but it should be much, much bigger, and this should be much smaller and clearly up high as the exponent. So please press pause and give it a try. When you press play, I will continue discussing the steps to solving this equation. So I know that 5 and log base 5 cancel. Those are inverse operations. That leaves behind 3x plus 1 equals 25. I will subtract 1 from both sides. and we get 3x equals 24. To wrap this up, we will divide both sides by 3, and we arrive at x equals 8. But I know that I need to do a little bit more work because this is a logarithmic equation. Not a lot more work, just a little bit, and run a check to make sure that this isn't extraneous. So referring back to my original, it would be log base 5 of 3 times 8 plus 1. And I'm looking to see if this equals 2. Let's see what we have going on inside parentheses. 8 times 3 is 24, plus 1 is 25. So this becomes log base 5 of 25. Don't know. I mean, I do. But let's say I don't know. I'm like, I don't know. Well, I see log base 5 and I see 25. If I'm trying to use the knowledge of inverses that I have, can I rewrite 25 with a smaller base? And I'm hoping everybody's like, yes, I can. And I would say, you are right. Because 25 can be rewritten as 5 squared. Log base 5 of 5 cancels, or you remember you could see it as the product property, however you, the power property, however you like to see it. Log base 5 of 5 cancels, leaving behind that exponent, which was 2, and check it out. 2 equals 2. Our solution is real. Number 3. Log of 5x equals 2 minus log of x minus 1. Now, just a quick heads up, number 3, you are going to need a decent amount of space. So if you happen to just like write this at the bottom of another page, you might want to copy this over to the top of another page. Now, we are entering a situation where we have logs on both sides, but notice we have 2 minus this. So let's make a little note off to the side. When there are 2 log terms and a non-log term, what would our non-log term be here? Looking at that 2, that's our non-log term. Our strategy will be to move the logs to the same side and condense. Ooh, look at that word come back. So we're going to bring back our condensing knowledge as part of number 3. So first let's get all of our log terms on the same side. I will choose to add log of x minus 1 over, since log of 5x is already over here. That cancels. So now I have log of 5x plus log of x minus 1 equals 2. How do I condense addition? How do I condense addition? Thinking back to my properties, I remember that addition becomes multiplication, and remember, when we condense, you only have a single log term as a result. So this will become log of 5x times x minus 1 equals 2. So this was where we condensed. Once our log terms were on the same side, we condensed addition into multiplication here. Working on some algebra here, let's see, we can multiply this out. So what do we get once we distribute 5x? 5x times x is 5x squared. 5x, so we did 5x times x. And now 5x times negative 1 would be minus 5x equals 2. This log term is as isolated as it's going to get. There's nothing else I can simplify inside the argument. So how do I eliminate this log? What is the inverse of log? Well, to know that, we do need to recall that this is log base 10. So to reverse that using our math skills, we will use base 10 and raise both sides. Notice how big the 10 is and how I clearly made this exponent higher and smaller. What we do to one side, we do need to do to the other, so this becomes 10 squared on the right, raised both sides. 10 and log base 10 cancel, leaving behind 5x squared minus 5x equals 100. As of now, we are out of our logarithm knowledge and into our quadratic knowledge. So to solve quadratics, remember that we're going to look to get it set equal to 0, and then see if you can factor. So we will subtract 100 over to the other side. This becomes 5x squared minus 5x minus 100 equals 0. What am I going to do from here? Dig up that quadratic knowledge. Now 5, 5, and 100, those are kind of big numbers, but as I'm saying them out loud, 5, 5, and 100, are we possibly thinking of a GCF? Maybe. Well, 5, 5, and 100 are all divisible by 5. So we can factor out 5. What's left behind? Factoring out of 5, I will get x squared minus x minus 20 equals 0. And now I can factor the inside. 5 will stay on the outside. A is 1. So I'm looking for factors of negative 20 that add to negative 1. My winning factor pair would be 5 and 4. Which of those has to be negative to add to a negative 1? So I'm just going to set it up like this for now. I'm trying to multiply to a negative 20. One of these has to be negative, but that's good for me because to get a negative 1, when I add 5 and 4, 4 needs to be positive and 5 needs to be negative. To wrap this up, we will set x minus 5 equal to 0, x plus 4 equal to 0. Here we get x equals 5, and here we get x equals negative 4. Recall that because 5 is a constant, it has no variable associated with it, like let's say it said 5x, that would be different. 5 is just a constant that will stay. It's not part of our solution set. Are we done? Nope. Because we are solving logarithmic equations, we know that we need to check. So I don't have the ability to fit in the original and the solution at the top, but you should have it on your paper, so that should be good. So we're going to check one at a time. First I'm going to check x equals 5. I don't want to lose track, so I'm just going to literally put it right there. Plugging that into my original, it's going to be log of 5 times 5 equals 2 minus log of 5 minus 1. So that's going to be log of 25. That's kind of scrunched. Log of 25 equals 2 minus log of 4. There's really no other algebra I can do without my calculator here, and these don't, like if this said log of 25 equals log of 25, I'd be in good shape, but it doesn't. So I need to use my calculator. Please get a decimal approximation for the left side and then the right side. and we'll see if they are equal. Press pause until you have those, and then we can compare. For a log of 25, we get 1.398. And for 2 minus log of 4, we also get 1.398. So we're in good shape. X minus 5 checked out, all good. Now let's check x equals -4. That will be log of 5 times -4. Careful, like for me just now, that multiplication sign and the negative kind of scrunched, so be careful. 5 times -4 equals 2 minus log of -4 minus 1. We have log of -20 equals 2 minus the log of -5. Can we go any farther? Answer is no. I'm going to write yourself a little reminder. Cannot take log of negative numbers. That means that this answer is extraneous. So, -4 is no good. Cross it out. Underneath it, please write extraneous, which means the only real solution for number 3 is x equals 5. So this shows us the importance of the check, because before the check we thought we actually had 2 real answers when in reality we only have 1. Very good. Let's look at number 4. Number 4 says natural log of x plus 2 equals natural log of x minus 3 minus the natural log of x plus 1. Now looking at this, how many log terms do I have now? Now I've got 3. So I don't have a non-log term. Let me say that one more time. I do not have a non-log term. So if I tried to gather all of my natural log terms onto one side, that really wouldn't make much sense, because I would have all the natural log terms on one side and then 0 on the other side. So let's make a note. No non-log terms. Go straight to condensing. So let's see what that'll look like. Natural log of x plus 2 will stay. What does subtraction condense to? Bringing back that prior knowledge, we recall that subtraction condenses to division. Remember, we will only have a single log term. What's getting subtracted is what goes in our denominator. We have natural log on both sides. The inverse of natural log is base e. So I will raise both sides. And I'm doing my best to make the e huge, make that one even a little bigger right there, relative to the exponent. E and natural log cancel, e and natural log cancel, leaving behind x plus 2 equals x minus 3 divided by x plus 1. This might look a little similar to number 1, where notice how this canceling happens on each side. So once again, this is an optional step, only if you are okay with understanding how you can move from here directly to here. Me personally, when I did these out, I always did the optional step because it helped my brain to see it. but that's completely up to you. So I personally recommend still showing yourself this, but once again, if you're okay going from here to here, I'm okay with it too. Once we reach this step, we are not in log world anymore. We are purely in our algebra world. So to solve this, we are going to recall how to cross multiply. So 1 times x minus 3 gets me x minus 3. And then it's going to be x plus 2 times x plus 1. Please multiply out and combine like terms and get this quadratic set equal to 0. Please press pause and do that. Again, you're going to distribute, combine like terms, and get this set equal to 0. When you press play, we will see if our quadratics match. Please press pause now. Alright, let's see if we match. I got 0 equals x squared plus 2x plus 5. If we don't match, please press pause and compare our algebra. And if we are on the same page, that's great. Looking to see here that a is 1. So are there factors of 5 that add to 2? And the answer is definitely no, because the only factors of 5 are 1 and 5. So when it's not factorable, it does not mean that answers do not exist. It does mean we will need to use the quadratic formula. So here, a will be 1, b will be 2, and c will be 5, pulling the coefficients. Please press pause, and when you press play again, we will compare our quadratic formula work. So press pause now and run the quadratic formula, and we will check in with each other when you are done. Press pause now. And if you really didn't press pause, definitely press pause now. Thank you. See you back in a minute. Welcome back. Do we match? Do we match? So in this case, the quadratic formula did result in 2 imaginary solutions, but very well could have resulted in 2 real decimal answers. So never assume. Quadratic formula is a very powerful tool in the toolbox that will always work for us if we have a quadratic set equal to 0. Again, if our algebra doesn't match, please press pause and compare. Any questions, by all means, shoot me a remind. We do have 2 more examples to round out today's notes. Number 5 says log base 5 of log base 3 of x equals 0. Log base 5 of log base 3 of x equals 0. And I was like, man, that looks crazy. We have log of a log. Well, I always want to pay attention outside in. So for right now, I'm actually going to completely ignore what's on the inside. I do know in my toolbox that to get rid of log base 5, I can raise both sides to log base, to base 5. So I'm going to do that. What I do to one side, I have to do to the other. So this will be 5 to the 0. 5 and log base 5 cancel, leaving behind log base 3 of x equals 5 to the 0 is 1. Well, I've unlocked log base 3 of x, and it's equal to 1, and now we will repeat the same process. But this time, what base will we use? Well, I'm trying to do the inverse of log base 3, so now I will use 3 as a base. What we do to one side, we have to do to the other. 3 and log base 3 will cancel, leaving behind x equals 3 to the first, which is 3. Before we say we're done with this, we do need to run it through a check, so let's do that. It's going to be log base 5 of log base 3 of 3 equals 0. bringing back our properties, I know log base 3 of 3 equals 1, so this becomes log base 5 of 1. 0 is still on the right. And then again for my properties, I know log of 1, no matter the base, log of 1 is 0. 0 equals 0, check. So to actually check this one, we had to use properties twice. We used properties to know that that was 1. And then we used our properties again to know that that equals 0. Last example, number 6. Log base 2 of log base x of 64 equals 1. So before I move past, I just want to write a little strategy note, because I've been doing that off to the side. So strategy for this one, start outside. We looked at that log base 5 first. If you want to highlight that, you can. And the strategy for number 6 is going to be the same. Because once again, we have log of a log. So whenever we have log of a log, we will always start from the outside and work our way in. So if I'm trying to first pay attention to this, I'm not even looking at what's inside those parentheses. I know I'm going to use 2 as a base. Notice how much space I just gave myself. I want to be really clear with everything I'm doing so I don't make any silly mistakes. What I do to the left, I need to do to the right. Choosing to use 2 as a base is very good for us because 2 to the log base 2 cancels, leaving behind log base x of 64 equals 2. What am I going to do? How do I unlock log base x? What's the inverse of that? Well, no different than this was if the base was a number, we can use a variable as a base just like we would a number. So we will use x as a base. So it's going to be x to the log base x of 64 equals x squared. X and log base x cancel, leaving behind 64 equals x squared. Or we could have recalled rewriting from logarithmic to exponential form. Remember this? Circle the base and come around. X squared equals 64. Notice, x squared equals 64. So you have options. Both of these strategies will work. To finish solving for x, what are we going to do? We will take the square root of both sides and get x equals plus or minus 8. Before we can say we're all done, we do need to run the check. So let's check. I'm going to ask that you run the checks on your own, so press pause. When you're done, we will see if our checks match. So please press pause now and finish the checks on your own. When you press play, we will check answers with each other. So let's first compare our work for the check of x equals 8. And if anybody struggled, this is where we really are going to have to start recalling our prior knowledge, especially the inverse relationship, because to go from here to that first step, I had to realize that I could rewrite 64 as 8 squared. In log base 8 of 8 cancels, leaving behind 2. Log base 2 of 2 equals 1. So this is where that all of the knowledge from this last few days now becomes toolbox tools that we can use whenever they are needed, just like they were here. So x equals 8 does check. x equals negative 8 fails. Once again, recalling our prior knowledge, by definition of logs, those first definitions we wrote at the beginning of the section, we cannot have a negative base. So right away, as soon as it was written, I knew I was done and that x equals negative 8 is extraneous. So if we wanted to, we could actually kind of like split up these two answers over here and say that this one did work, this one failed and is extraneous. That wraps up our notes for today. Very nice job. Any questions on any of the solving or use of properties, by all means, please send me a question on Remind, and looking forward to practicing these new solving skills in our next class. Have a good night, everybody.